easy. So yeah, we want to basically isolate the vector part. So now we can subtract them to get A as this vector minus the eigenvalue times by the identity matrix, and that will be equal to 0 because it's just algebra. It's just algebraic manipulation. And before I go deeper, I'll explain what the identity matrix is. It is literally just a square matrix of ones going diagonally. And this is like, what's it called? Basically, this is like the one version of multiplication. So for matrix multiplication, this is like the one. This is what makes everything the same. So now with this part, what we can do is factor out the vector. It's more important. Alright, do you get that, Victor? Alright, cool, sweet. Does anyone else not get that or need me to go over something? So you got 40%. No, don't skip the thing. It's so free. It's so free. And all the answers are basically in the WhatsApp chat. So it's just easy marks. I would suggest no one to skip the FSAD assignment because it's trivial. Albeit it's a bit of a task. No, I'm not the one who did that. I figured out all on my own. Plus have no evidence. I'm just saying you theoretically could if you were not as morally inclined and morally perfect as I am. Whoa, Ash, I wouldn't do that. It's your chat, so. Okay, let's get back on topic before we start yapping again. So yeah, we left off with this identity, which we're gonna use to start calculating things now. So first, I'll pull up a 2x2 matrix. Oh, the whole thing's pink. Oh, okay, it stopped. That's good. I'm gonna put this line. This line is like the old stuff. Alright, now for the matrix. So let's set A to be this matrix we're gonna figure out. And it will be 2, 1, 4, 5. Okay, simple. And now to get the version that we're gonna use, we're gonna have to subtract the identity matrix times by the eigenvalue, which usually gets skipped in the explanation, but I'll just write it down to make it easier. So this is what we're subtracting against it to help us figure out the eigenvalue and then the vector. So A minus all that would be 2, that looks like a Z. 2 minus lambda 1 and 4 5 minus lambda. And don't forget we have to get the determinant. I should probably have said that. But yeah, this is the part we're doing now. Alright, so has anyone lost there? Just type in the chat if you are. I can't find the lab solution. My scroll is too broken to get out again. Just rejoin it, I guess. Although it sounds like an issue in the skills department. Okay, I'm good. All right, there you go. Skill issue resolved. Glad to hear it. All right. Anyway, so going on from this, we got to figure out the determinant of this thing, which is mega easy. All we have to do is classic formula, which is a. Okay, it's it's bigger now for some reason. I didn't change it, but that's okay. AD minus BC, or the classic cross multiplication, because that is what we're doing, and we're minusing them, as shown up here. All right, I'm gonna clear this thing now because I think everyone's on the same page. Or I might have to. I'll rewrite the vector. There's an easier way to clear all this. This was it. Spam. Okay, this is what we're working with. 2 minus lambda. 1, 4, 5 minus lambda. The determinant is simply 2 minus lambda times by 5 minus lambda. And that would be minus 4. So multiplying these like that. Multiplying these like that. Okay, that makes that really hard to see. Alright, hello, Mr. Newcomer. If you could mute your mic, that'd be good. Okay, he's also deafened me out by accident. Nice, nice. Alright, so all we gotta do is just basically make this into a pure quadratic over here of lambda. So all we'll do is expand the brackets out and integrate the minus 4 into the quadratic. So, negative lambda squared, it's normal lambda squared, just cross multiply basically. I can't really bother to explain this, because you probably all know it. Minus 4, which equals to lambda, holy crap, lambda squared minus 7 lambda, what's that, plus 6. Alright, I should probably write with a smaller font size. Okay, I don't have to do that, so I can't be bothered. Oh shit, oh, what? Oh, that's so easy. Okay, so is anyone stuck on this, like how I got to this quadratic over here? If you are, just shout. Alright, nice. Cool, cool. Yeah, after this, I'm doing 3 by 3 matrix, which is going to be a lot longer than this one. So we'll see how that works. But undo. The most attendance. Oh, well, it looks like there's a lot of people here, to be fair. I don't know why, but it's kind of easy. So from that thing we just got, we have the thing lambda squared minus 7 lambda plus 6. And he remembers those. That's what I'm saying. I didn't like his lectures. He just waffled the whole thing. I couldn't pay attention. Oh, I've accidentally changed the size again. Alright, so you have lambda squared. Yeah, so if you can't tell like by looking, which is fair, the solution is lambda minus 6 minus 1, because minus 6 and minus 1 add to minus 7, but multiply to make 6. And this gives us solutions. So we just have two solutions for lambda. because it's a quadratic. And by the way, the quadratics that we've got, this one, it's known as the characteristic polynomial of the matrix, just in case, I don't know, the exam asks that or something. But yeah, so we have lambda 1, which is equal to whichever one we want, so 6. Because remember, this has to equal to 0. Oh yeah, I know. I was gonna teach that hooks, but the thing is, like, imagine you do that in the exam, but they want your working, and you just write down like some short square formula. That's why I didn't want to teach it. So we have the second lambda, second eigenvalue, and that works out to be 1. It's nice. So moving on to the second part, we all love algebra. See that. Right, moving on to the second part. Now that we have our eigenvalues, we have to work out the vector. And this is where Victor's, I think it was Victor's lecture that was last, but essentially we're gonna have to use Gaussian elimination. So does anyone not get all that stuff, how we got to the eigenvalues? It was Danny's. Oh, mad. But yeah, anyway. So to get to, so I'll write down the equation again. So we have currently solved, so we've given this matrix A, that's what we're given, and we've solved the eigenvalues, so we know which eigenvalues will compute to give us the same vector. But now we are looking to calculate this value. So how do we do that? Gaussian elimination, as I said. So what we'll do is we'll substitute one of the eigenvalues. Let's just take, I don't know, the second one or something. And yeah, so we have an eigenvalue of 1. So this will mean we have to recompute the matrix. And all we do is have 2 minus 1 here. 1, 4, and then a 5 minus 1. Which will give us 1, 1, 4, 4. Which is very symmetrical looking and it makes me happy. So yeah, anyway, we need to do the row echelon stuff. So I think how we do this, I might need to be corrected because my memory's not so solid on this one. So both of these come out to be 0 because, well, that's essentially what this is doing. And we need to get values of x. And these values of x are they're just what's in the matrix. Actually, I wrote v1 and v2 because that's confusing. Now, oh, how do you do this part? I'm not sure if I remember. Let me think. Let me cook. 2 by 2 matrix. I think what we do is, yeah, we might just have to subtract 1. So the thing about this is that both of these rows are linearly dependent. So one of these will end up being completely 0. So let's take the second row, for example. So this one, R2. We will minus, let's say, 4 of row 1. So this will give us, let's cancel this out. There's gotta be a better way of doing this, but oh well. it will have 1, 1, 4, 4. Yep, and this will go to 1, 1, not, because we subtracted, so we have R2 just equal to R2 minus 4 times row 1. And this gets us closer to the echelon form, which is our goal for figuring out the individual variables in the vector. So at the end, this is what our matrix looks like for figuring out. The bird kicked me. Oh, I don't know, he kicked you, but it wasn't me. So this gives us the equation v1 plus v2 equals 0. So all this means is that v1 is equal to minus v2. And essentially for this vector, we can make up like any value. You can just pull any value out of our ass because these are just relative to each other. So let's just take v1 to be 1 because that's easy. So we have officially figured out for a lambda value, so for the eigenvalue of 1, a vector can just be 1 minus 1, basically. So yeah, that's a complete dissection of a 2 by 2 matrix. So does anyone not get that? Is anyone stuck on this Gaussian elimination? I use some time. I use you guys some time as an excuse to drink the rest of my tea. Where did v1 equals 1? Oh yeah, that's a fair question. I made that up because it does not matter. Making it annoying to move the recording around. Sorry. What happens to the eigenvalues vectors of a matrix when multiplied by another matrix? Eigenvalue. I have no idea what it's asking. Oh, so if you're multiplying two matrices? I have no idea. But I will soon move on to 3 by 3 matrix. Alright, I'm gonna keep it in the bottom half and I will decrease my font size. So this one I'll try and make it as painless as possible because it's really long to do. But it is essentially the same thing as last time. Alright, so I'll just bring us to this point. Oh, I changed the color again. But yeah, this is what we're doing, but now with a 3 by 3 matrix. So I will now draw the 3 by 3 matrix. Alright, let's pull up the example. So we will have 2 minus lambda, 1 and 3. I'm also skipping the subtract lambda step because there is no point in going over the same thing. Yeah, 3, 3, 20. Okay, this 3 is looking crazy, but I think you can see it's a 3, hopefully. So this is our A, this is our matrix, by which the vector v is being multiplied. So to figure this one out, we have to get the determinant of this big boy over here. And the way we do that is kind of weird, but for all values in this top row, so this one, and this one, we have to basically select them out of the group, delete all these columns and rows that basically pertain to the position where this value is. So for 2 minus lambda, we delete all the first row in the first column that isn't it, and also it technically. It's the same for 1, so if we to do 1, we delete the rest of this row and the rest of this column. And we would apply our 2 by 2 determinant rule to these. So I'll just go through it manually, and you can see what I'm on about, even if you don't understand what I said. So we'll select this value, starting from the first one, delete these, as I said, and now we can apply the determinant rule here. But one caveat is that you must multiply this top diagonal bit by the determinant. And there's also a special order for the minuses, but I'll get onto that. So for this, it's just multiply this by, it's going to be big, I think. Yep, 2 minus lambda times by 20 lambda is minus 9. So now our first thing that we need to note is that the sign we're going to be using, it's a minus. This right here, it's a minus. And the next one we're going to use, is going to be a plus sign. And it interchanges between those two when you do this calculation. So for the second one we're doing, we select 1, delete this, and delete these ones. So this is going to get harder and harder to see, but hopefully you can understand when we do this. So we'll have 1 here. And the good thing about this is that you only have to do this complicated step for everything in the top row, and not for every single one. That would be so hard on my brain. So yeah, delete this part, delete this part. So we have the determinant 1, 3. So yeah, we have 1 times by 20 minus lambda minus 9. And the next thing, this will be plus, because as I said, we switch the sign. And the last part we do is 3, which you can barely see at this point, but here it is. We delete this and we delete this part. So this part we'll multiply by 3. And I won't go through the entire reduction of this big equation here because I've already got it written down to avoid that thing. It's going to take up too much time. So when we delete 3, yep, delete this part, delete this part. 1 times by 3, 3. 3 minus 3 by 2 minus lambda. Yep. Yeah, that looks about right. So does anyone not get this massive chunk of numbers? Like, is this, like, have I lost anyone, basically? If so, just type in the study VC chat. I'll try my best. Alright, good on your end. Alright, fair enough if everyone if no one has any questions, that's fine. We will now delete all of this. And then skip to the part where it gives us a nice equation. Well, as nice as a order 3 polynomial can get. Go. Ah, alright, so the entire thing that did, the determinant of that 3 by 3 matrix we worked out, that works out to be lambda cubed plus 24 lambda squared minus 65 lambda plus 42. And don't forget that is equal to big fat 0. So there's not really like I can't really show you the quadratic formula and like solve this for you, but the solutions when you plug them into like an online calculator or something, it would be 1, 2, and 21. This is the solutions to this order 3 polynomial we have here. So now what we're going to do is we are going to we're going to have to do Gaussian elimination to find one of the vectors, because remember that there's a different vector for each eigenvalue we have. There's different eigenvalues corresponds to different vectors. So that's all. So let's just take like imagine we get an exam question. It's like, oh, give us the eigenvector for which eigenvalue 2 corresponds to. Happens when you use a 5 by 5 matrix because it isn't an equation for a quintic. I actually have no idea, but that would be very cool. I'm sure it'd be very interesting looking and much more monstrous than what I'm doing. 9 by 5 matrix. I would ponder on it, but I would like to get through the rest of this 3 by 3 matrix. Because I am using up people's time. But, okay. The last part of this, getting the vector. We will now write down our vector again. Oh, I changed the slice again. But this time we're substituting the second lambda for this one, which is equal to 2. So it should be 2 minus 2. 1, 3. Oh, this looks like it's going to be nice. And then 2 minus lambda again, which is 0, 3. And then 3, 3, 20 minus lambda. Okay, not the best written. But essentially, I'm going to put this into another one now. So this would be 0, 1, 3. And this would be the first element of the vector. 1, 0, 3. Second element. And then 3, 3. It's 20 minus lambda, so that's 18. You can complete it. And so what these represent is basically a system of linear equations. So all this means it's like one big multiple simultaneous equation. So we'd have V2, so 1 V2 plus 3 V3 is equal to 0, and basically 2 more sets of those with different values that we can use. So we're going to start out by reducing this, thinking kind of like close to row echelon form. So first thing I'm going to work on is row 3 here, this one. I think the first thing I'll try is row 3 minus 3 times row 1 minus 3 times row 2. Because we can see here from row 1, this has one multiple of v1, v2, which is the second element of the vector, and subtracting that 3 times will make this 0, and subtracting v1, this one here, and row 2 3 times will make this one 0. So this will transform our matrix. And also I'm going to shuffle these around just so you can get the echelon form right, but it's not something you have to really do. It just looks, it's less confusing, basically. So this would be the second row, which is now the first. This was the first and it's now the second. And this is a modified third row. This is 0, this is 0. This would be 3 times 8. Oh, it would be 0. Interesting. So yeah, this is the solution that we're left off with once we've done the Gaussian elimination. So is anyone lost on how I got to this point right here? And if so, you can just message in the chat. Even if you like half get it, but don't understand where I got to some places, just ask. So I'll leave that for a minute, let the beautiful knowledge soak in. Get it? Nice. Danny taught you well. Yeah. I'm gonna have a beautiful push day at the gym after this. Alright, so the next step, we're so close to being done with this bloody 3x3 matrix. So I wish I could delete everything and keep this, but I don't think I can, so I'm gonna use the remaining space. Actually, no, screw it. With it. I will do that. I'll just memorize it. Okay, 103.013. I think that's what it looked like. Oh, okay. And forget this is our eigenvalue. So this is only for one of the eigenvalues. If you were to do all 3 of them, you just have to do this calculation 3 times. Because as I said, they're different vectors for each one, so you have to figure out. But I think it was 103.013. Last one was all zeroed out. And each one of these equations comes to 0. And I'll write each element of the vector that we're figuring out. So for the first one, this first row here, I'll divide them. First one, we get this v1 plus 3 times v3 equals to 0. And now to get equations and make them relative to each other, you can just subtract it from both sides. This will give us v1 equals minus 3v3. And I suppose we can make up a value for v1 or v3. Anything. So yeah, let's just say, let's take v1 to v1 again. So once again, I've completely made this up, but it does not matter. So this would mean V3 would have to be, let's see. Yeah, so if we divide this by both sides, it would be minus a third. That's what V3 would be. And now we have the second equation. So where it is V2 is equal to minus 3. So I basically just skipped the step here. But all this means is that it's the same thing I did with V1, but it's V2. Because as you can see here, there's one V1 over here. And there was three V3s. So it's the same situation, but different variables. So what this means is that V1 and V2 can just take the same value because they'll have the same relationship with V3 essentially. So I've done this in a roundabout way because I'm out of practice with this, I think. But this essentially just gives us 1, 1, and then minus a third. Or if you prefer, you can just scale all these up because once again the value does not really matter. 3, 3, minus 1. And that is our matrix. So don't have any questions about that. So we're literally done, that's it. So any questions about anything that I've done? Yeah, take that as a no. Okay, thank you everyone. Thank you for recording Deadlock Chamber. It's very nice of you. Sensei. Awesome. Who is carrying? Alright, see yous.